This is just a little bit of practice. I promised I would put up a problem that kind of tied together the last thing that we did in class today, which is look at electron configuration and how we were able to compare that to the orbital diagrams that we drew. So I'm just going to do two problems. And the first one is we're going to write the electron configuration and the orbital diagram for silicon, and then we're going to do the same thing for oxygen. So first, let's take silicon. Silicon is an element that has an atomic number of 14. So that means it has 14 electrons. So our electron configuration tells us where those electrons can be found. And if we write that out in terms of what we did in the last semester, you can see that we've got 1s2, 2s2, 2p6, 3s2, and 3p2. So we've got three different energy levels here. We've got 1, we've got 2, we've got 3. So if I write the orbital diagram for this, what I'm going to do is write all three energy levels with each of its orbitals written out individually. And then I'm going to show the individual electrons as arrows in each one of those orbitals. And remember, we say we have a few rules here. The first one is we occupy the lowest orbital, the lowest energy orbitals first. So all the orbitals in energy shell 1 are going to be occupied before we go to 2. And those are going to be occupied before we go to 3. At the same time, all of the s suborbitals are going to be occupied in each shell before we go up to p, and all of the p's have to be occupied before we go up to d, etc., etc. And we're going to look at exceptions to those later. Based on this electron configuration for silicon, let us write out what the orbital diagram would look like. Now, the orbital diagram is based on those boxes that we drew today, and they simply just make and assign a box for each energy level in orbital. So we've got an orbital that corresponds to 1s. Then in the second energy shell, we're going to have one that corresponds to 2s. Oops, let's get rid of that. Then we've got in the second energy shell, we also have 3p orbitals. So this is going to be 2p. Then we move up to the third energy level. We start out with the 3s orbital. Then we can have a 3p. And over here we can go up to 3d, 4s, 4p, 4d, 4f, etc. But for right now, I think this is enough orbitals to fill for all of the electrons to fill. So we have 14 electrons, and just like we have here in the electron configuration, we're going to fill individual electrons first. Opposite spin, remember. So we have 14 of them, so we can keep going up until we get to higher energy levels. So we've got 2, 4. Let's fill all of these individually before we start to pair them up. So we've got 2, 4, 5, 6, 7. So now we come back and start pairing them up. That's 8, 9, 10. Now we move up to the next energy level. This is 11. Before we can go up to 3p, we have to completely finish filling up 3s. So that's 12. And now we have 2 more electrons that have to go in the 3p. We're not going to pair those up, remember. We have to fill each sublevel with parallel spin electrons first before we can come back and pair them up with electrons of opposite spin. So this is the orbital diagram for the silicon atom. It has 2 electrons in the 1s, same thing as we see here in the electron configuration. It has 2 electrons in the 2s. It has 6 electrons in the 2p. It has 2 electrons in the 3s shell, and it has 2 electrons in the 3p. What we see is that is different from the electron configuration is that we can see how these electrons exist. We can see that these are 2 unpaired electrons. And we'll get into all of that later on as we get into the chapter. But this is how the relationship between electron configuration and the orbital diagram looks. Okay, so let's do quickly one more. Let's do the oxygen. And I'm going to do this one much more quickly than I did the other one. All right. Oxygen, colors here, is an element on the periodic table with 8 electrons, and it's okay. And so to write the electron configuration for oxygen, it is 1s2, 2s2, 2p4. So that's 8 electrons total. To write the orbital diagram notation for oxygen, we start off with our boxes of all the allowed orbital energy levels. Okay, so we have 8 electrons to fill. We start here, 1. Before we move to 2s, we have to completely finish filling 1s. So that's 2. Then we move up to 2s. Before we move to 2p, we have to completely finish filling up 2s. That's 4 electrons total. Now we have 4 more electrons to go. So we're going to put these in singly with parallel spins before we start to pair them up. Okay, so that's 2, 4, 5, 6, 7. Now we have 1 more electron, and now we can't go up to 3s. We have to actually completely finish filling up 2p first. And so we come back and start pairing up the spins in opposite directions of the electron for the electrons. Now, as we can see, you still have 2 electrons in the 1s. You still have 2 electrons in the 2s, and you still have 4 electrons in the 2p shell. And we can see here that we have 2 unpaired electrons in the 2p sublevel. Like I said, that's going to come into play later on. But those are just 2 examples of the last thing that we did in class, and I encourage you to practice those problems at the back of the book if you want to work a couple of them yourself and get some practice. I think the let's see what's a good problem for you to work. A good problem for you to work is problem number 42, A, and problem number 42D, problem number 43A, and 43D. Those are good problems for you to practice on for right now, based on this topic. And then we'll continue some different rules that relate to electron configuration and molecular orbital theory, atomic orbitals. Okay, so just wanted to give you those little practice problems.